Welcome to Space Dreams documentary, where tonight we enter the first Magnetar birth caught unfolding live. A brilliant star dies outwardly, yet something deeper seems to wake beneath the expanding ruin. The explosion stops looking terminal when its light behaves like a hidden engine switching on inside. Some supernovae burn too long and too strangely for ordinary radioactive wreckage to explain alone. That excess brightness opens a debt as though the blast spends energy no corpse should own. Superluminous events exceed what standard collapse models comfortably finance, leaving missing power written across the sky. The real driver may be the remnant itself, a newborn neutron star feeding fresh power outward. In a Magnetar newborn rotation becomes stored violence, an energy reservoir wound to frightening extremes. Spin alone is not the whole story, because geometry decides where that violence can actually go. Its magnetic field channels torque heating and escape reshaping matter instead of merely decorating collapse. Relativity enters when frame dragging twists nearby. Fallback, changing how matter circles, falls and survives. Some debris neither escapes nor vanishes, but returns, circularizes, and forms an impossible disk around devastation. Now the wreckage becomes a system with returning layers, feeding the object that shattered them. Fallback is not passive debris. It can break, bury, feed, or amplify the newborn Magnetar. The light curve starts speaking when smooth fading breaks into humps, delays, and possible chirping structure. Those rhythms turn brightness into evidence, shifting the story from spectacle toward a measured, unfolding experiment. What astonishes astronomers is timing, because the Magnetar's emergence is inferred while the system still changes. Easy models each explain fragments, yet none cleanly matches the luminosity, cadence, and full timing. Stellar death becomes negotiation, where gravity, rotation, magnetism, and returning matter keep rewriting the outcome. Claiming a first real-time birth demands caution because rare imposters can hide inside incomplete data. Watching a Magnetar emerge reveals some supernovae as factories where extreme physics briefly shines uncovered. Please like, subscribe, and thank you for listening as death's first strange light begins now. A star is supposed to die all at once. Its core fails. Its outer layers are blown away, the light surges, and then the wreckage begins, the long, honest work of fading. That is the simple version. It is also the version that breaks the moment a superluminous supernova refuses to behave. Because sometimes the brillide unveiling a death so violent that it briefly hides the birth of something in tradition at the center of SN 2024A FAV, a stellar explosion first spotted in December 2024, about 1 billion light-years from Earth. An event so luminous that for a time it outshines the combined light of the Milky Way. A normal supernova is already difficult to comprehend. It marks the collapse of a massive star's core after nuclear fusion can no longer hold gravity back, and in that collapse, the inner star is crushed so hard that matter itself is rewritten. Protons and electrons are forced together into neutrons. The core shrinks from something like the size of a world to something closer to the size of a city. If too much mass is trapped there, the collapse keeps going, and a black hole forms. If the conditions are just short of that abyss, what survives is a neutron star, one of the densest objects the universe allows to remain visible. But the obvious explanation is not the real one. The explosion matters, yes. The collapsing core matters, yes. Yet the story on the surface is smaller than the story underneath. Because in some rare cases, the object left behind does not merely survive the catastrophe. It takes control of it. For years, astronomers have argued over a strange subclass of stellar explosions called superluminous supernova blasts that shine roughly 10 to 100 times brighter than ordinary supernova and stay bright far longer than standard models comfortably explain. The old intuition says the answer should be bigger. Star, bigger blast, more debris, more light. That sounds reasonable from a distance. It stops sounding reasonable once the accounting begins. Supernova light is not free. It has to be paid for by radioactive decay, by shock, by interaction with surrounding gas, by some mechanism that can keep energy moving outward long after the first detonation. In many ordinary explosions, nickel forged in the blast helps sustain the afterglow. In these monsters, the bill grows too large. The light lasts too long. The engine seems too powerful for the visible wreckage alone. So the hidden question changes. The mystery is not simply why the star exploded. Massive stars explode. The mystery is why the light behaves as if something inside the ruin is still working. That is where the idea of a magnetar enters the story, and it enters with unnerving force. A magnetar is a neutron star with a magnetic field so intense that familiar comparisons stop being useful. It is also born spinning at enormous speed, in some cases hundreds of times each second, which means it begins life carrying a reservoir of rotational energy that is almost absurd in scale. If even a fraction of that energy is transferred into the expanding debris of the supernova, the brightness of the explosion can be amplified far beyond what radioactive ash alone could sustain. This idea was proposed years ago as a solution to the puzzle of superluminous supernova. It was elegant. It was powerful. It was not yet proven. The problem was never that the theory sounded impossible. The problem was that nature had not clearly shown its hand. Superluminous events were rare. Their light curves were messy. Competing explanations remained alive. Circumstellar material could also brighten an explosion. So could unusual ejector structure. So could combinations of effects that imitate one another from a great distance. In astronomy, plausibility is not victory. The universe often tolerates more than one story until better evidence arrives. Then SN 2024 AFAV did something dangerous. It did not merely blaze. It flickered with structure. Over roughly 200 days, its light did not decline in the smooth, exhausted way expected of a fireball coasting into darkness. It rose, lingered, and undulated. The pattern was not random enough to ignore and not simple enough to dismiss. The bumps arrived like signals from machinery hidden behind smoke, and with each fluctuation, the easy version of stellar death became harder to defend. Because a plain explosion fades, a system evolves, a dead star cools, an engine modulates. This distinction is everything. It is the difference between aftermath and activity, between debris and control, between a corpse and a newborn power source still negotiating with the wreckage around it. That is why this event matters beyond its brightness. It is not just one more spectacular detonation in a crowded universe. It is a case in which the light itself begins to act like evidence from the center, as though the remnant is not buried deeply enough to stay silent. And that changes the emotional scale of the story. We are no longer watching only the destruction of a massive star. We are watching a possible first glimpse of a magnetar coming into being, while the violence of its birth is still unfolding around it. A birth disguised as an ending. A compact object hidden inside expanding fire. A neutron star not as leftover ash, but as the mechanism rewriting the meaning of the blast that made it. Yet even that is not deep enough. Because if this explosion really is powered by a newborn magnetar, then the next question is harder, not easier. It is not enough to say the engine exists. We have to ask how such an engine can produce light, so excessive, so prolonged, and so strangely structured that it forces theorists beyond ordinary collapse physics and into a regime where rotation, magnetic torque, infouling debris, and even the dragging of space-time itself begin to matter. The explosion is real. The newborn object is real. But the true scandal is the budget. Why these supernovae shine beyond expectation is where the real descent begins. The first problem with a superluminous supernova is that it looks like an answer when it is really a refusal. You see an explosion of impossible brightness, and the mind reaches for the oldest explanation in astronomy. More light must mean more violence, a bigger blast, a bigger star, more fuel burned, more debris heated, more radiation escaping into space. That instinct is understandable. It is also where the misunderstanding begins, because these events do not merely shine more than ordinary supernova. They strain the logic of how a supernova is supposed to pay for its own light. In a normal stellar explosion, the broad outline is difficult but stable. The star dies, the shock tears outward radioactive elements forged in the blast decay, and the expanding debris glows as it cools. The brightness rises and falls according to a physical budget. Energy is injected, trapped, reprocessed, and gradually released. There are surprises at the edges, but the accounting more or less closes. Superluminous supernovae are where the arithmetic starts to look dishonest. These explosions can appear tens of times brighter than familiar core collapse events, and some remain conspicuously luminous for far longer than the easy models prefer. That is not a cosmetic difference. It is a structural accusation. Because when the light becomes that extreme, every explanation has to answer the same brutal question. Where does the energy actually come from? The obvious reply is radioactive nickel. That answer works beautifully in many supernovae because nickel-56 decays into cobalt and then iron releasing energy that helps sustain the fading glow. But for the brightest superluminous events, the required nickel mass becomes absurdly high, sometimes so high that the model begins to resemble a bookkeeping trick instead of a plausible star. You can force the numbers on paper. You cannot force nature to like them. The real problem is not simply producing a brilliant flash. Astrophysical explosions can do that. The real problem is sustaining enormous luminosity over time without demanding a progenitor and an explosion mechanism that collapse under their own improbability. That is why the class itself was so destabilizing when astronomers began to recognize it clearly. These were not just rare bright supernovae sitting at the upper edge of a familiar distribution. They behaved like a separate challenge. Many were hydrogen-poor, meaning they lacked one of the usual signatures of a massive star still wrapped in thick outer gas. Many showed light curves, whose shapes suggested that something more than one brief release of energy was involved. Some rose slowly, some lingered, some developed bumps and shoulders and secondary structure that felt less like the clean cooling of debris and more like the visible trace of a hidden negotiation between expanding matter and a central engine. This is where the category stops being descriptive and becomes philosophical. Because an ordinary supernova invites the observer to think in terms of event. A star explodes. A blast happens. The wreckage fades. A superluminous supernova forces the observer to think in terms of process. Something continues. Something interacts. Something keeps rewriting the visible outcome after the initial catastrophe should already be over. SN. 2024. FAV matters because it sharpens that discomfort. It is not merely bright in the way a headline can be bright. It is troublesome in sequence. Its luminosity is accompanied by structure, by behavior over time that makes a simple detonation look less like a full explanation and more like an opening move. That is why brightness alone is not the true story. Brightness is what attracts attention. Persistence is what creates suspicion. Variation is what begins to look like evidence. Once those three appear together, the explosion ceases to be a single act and starts to resemble a system exposing itself piece by piece. The tension grows when scale is made visible. A supernova already releases more energy in a short span than the sun radiates over billions of years. A superluminous supernova pushes that spectacle into a harsher regime, not necessarily by being the most energetic in every possible sense, but by channeling extraordinary amounts of power into visible light with a timing and efficiency that ordinary assumptions do not comfortably explain. That difference matters. In astrophysics, light is not just a decoration on top of the event. Light is the event translated. It is how buried physics announces itself across cosmic distance. So when the light curve looks wrong, what it really means is that the underlying mechanism may also be wrong, or at least incomplete in the model being used to interpret it. The accepted explanation is not the real one, or rather, it is only part of the real one. Shock heating can contribute. Radioactive decay can contribute. Interaction with material previously shed by the star can contribute. But there comes a point where piling partial answers together starts to feel less like understanding and more like diplomacy. Each ingredient explains a portion. None naturally commands the whole pattern. And when an event begins to show modulations instead of a smooth retreat, the question deepens again. Not just what powers the light, but what sculpts it. Because sculpting implies control. Control implies geometry rotation, magnetic structure, delayed injection, asymmetry, fallback, or some other mechanism with memory. A cooling cloud has no memory. An engine does. This is why the easy picture of stellar death fails here. It imagines collapse as a terminal act, a one-way descent from star to remnant. But some deaths are less terminal than they appear. The remnant may not sit passively beneath the ejector like a buried stone. It may continue to spend rotational energy, torque the surrounding matter, alter the rate at which energy is deposited, and leave fingerprints on the escaping light. The explosion on the surface is still real. The blast wave still matters. Yet the larger truth is that the event may no longer belong entirely to the explosion that began it. It may belong to the compact object that survives inside it. And that turns the puzzle from one of brightness into one of architecture. A superluminous supernova is not difficult because it is big. The universe is full of big things. It is difficult because it forces a transition from the language of detonation to the language of machinery. It asks whether what we are seeing is not just an overpowered ending, but an ending commandeered by a newborn engine. And once that possibility is taken seriously, the next problem becomes unavoidable. If ordinary stellar debris cannot easily pay the bill, then the source of the excess light must come from a reserve far more compact, far more violent, and far more disciplined than the blast itself. The answer seems clear until the scale becomes visible. A superluminous supernova looks at first glance like the natural upper end of a familiar process, as though nature has simply taken an ordinary stellar death and turned the dial higher. More mass, more heat, more light. But once the numbers are forced to stand still long enough to be examined, the simplicity evaporates. Because these explosions do not just exceed expectation by a little. They threaten the energy logic that makes supernovae intelligible at all. An ordinary core collapse supernova is already one of the most violent events in the cosmos, but most of its energy vanishes into neutrinos and kinetic expansion, not visible brilliance. Only a controlled fraction emerges as light. That fraction is precious. It depends on how energy is deposited into the ejector, how long radiation remains trapped, how fast the debris expands, how opaque the material stays, and whether any additional power source continues feeding the outward glow after the first shock has passed. In a superluminous event, all of those terms begin to harden into demands. The luminosity is too large to ignore the duration, too extended to wave away, and the spectral behavior too structured to treat as a simple giant flash. This is why the category matters so much. It is not just that these objects are bright, it is that they are bright in a way that pressures every underlying assumption about where a supernova's visible power comes from. For a time, one tempting answer seemed to offer relief. Perhaps some of the brightest events were pair instability supernova explosions of exceptionally massive stars, in which the core grows so hot that light itself helps trigger catastrophe. High-energy photons begin converting into electron-positron pairs. Pressure support drops. The core partially collapses. Oxygen burns explosively, and the star can be torn apart without leaving behind a compact remnant. It is a magnificent mechanism, and in the right circumstances, it can produce enormous quantities of radioactive nickel, enough to power an unusually luminous light curve. On paper, that sounds close to what is needed. In practice, it solves less than it promises. Pair instability events should follow fairly specific mass ranges and leave fairly specific photometric and spectroscopic signatures. Some candidate events exist, yet many hydrogen-poor superluminous supernova rise and fade on timescales, and with line features that do not sit comfortably inside that box. Worse, the pair instability solution carries its own price. It demands progenitors of extraordinary mass under conditions that may be uncommon, and it does not naturally explain every internal irregularity in the light curves of the most troublesome cases. So, the elegant answer remains real but partial. It can explain some roads through the landscape. It does not explain the whole terrain. Another candidate is circumstellar interaction. A star may throw off shells of gas before it dies, and when the supernova ejector slams into that material, kinetic energy can be converted into light with ruthless efficiency. This too is physically sound. In hydrogen-rich events, the evidence can be dramatic and direct. But many of the most famous superluminous supernova are hydrogen-poor, which means the surrounding environment either has to be unusually configured, unusually stripped, or unusually difficult to detect. Again, the answer works, but at a cost. It starts requiring hidden structures, placed just so shells at the right distances, masses in the right distribution and interactions, fine-tuned enough to mimic a sustained internal power source. The story becomes less convincing, not because any one ingredient is impossible, but because too many ingredients begin to feel custom-built for too many separate cases. That is when the deeper problem finally becomes visible. The real challenge is not explaining one bright moment. It is explaining a sustained luminous history in which the ejector seems repeatedly supplied with fresh influence after the initial detonation should have settled into decline. Light curves are not merely graphs here. They are records of pressure, diffusion, opacity, geometry, and timing. They tell us when energy enters the system how deeply it is buried, how efficiently it thermalizes, and whether the source behaves like a fading cache of radioactive ash or like a compact machine with reserves still being spent. In many superluminous events, the light does not behave like a fortune inherited all at once. It behaves like income. That difference is devastating to the easy picture, because inherited energy runs down. Injected energy can reshape the entire visible evolution. It can delay decline, flatten phases that should steepen, and create secondary structures that a one-time blast alone struggles to produce. SN 2024. AFAV pushes this discomfort into sharper form because its brightness is not content with being excessive. It also appears organized. The signal does not merely overwhelm, it hints. The surface interpretation still says explosion, but the deeper interpretation begins to say regulation, as though some compact source beneath the ejector is not just contributing power, but governing when and how that power leaks into view. And that is where the argument changes from magnitude to mechanism. Once a supernova becomes too bright for nickel, too structured for a simple fireball, and too persistent for a single impulsive release, the remaining options become more demanding. Either the star prepared an extraordinary external environment before death, or the remnant left behind is not passive. Either the visible outcome is driven by collision with previously hidden material, or a newborn compact object is continuing to pump energy outward from the center. The first possibility preserves the old emotional structure of stellar death. The star sets the stage, then dies, and the aftermath plays out in the debris it already arranged. The second possibility is more disturbing. It means the death of the star does not conclude the event. It creates an engine. It means the remnant is not an epilogue, it is the next act. And if that is true, then the scale of the explosion is no longer the most important thing about it. The most important thing is the object buried inside the wreckage, the city-sized survivor with enough rotational energy and magnetic violence to outshine the comfortable explanations that came before it. That is the larger truth superluminous supernova keep forcing into view. Their light is too expensive for ordinary death. Something smaller, denser, and more terrifying has to be paying the bill. The remnant is supposed to be the quiet part of the story. After the star tears itself open, after the shock escapes, after the ejector begins racing outward, the object left at the center is often imagined as a kind of grave marker, a compact residue that matters in principle, but not in the visible drama of the explosion itself. That picture works for many stellar deaths. It fails completely if the remnant is a newborn Magnetar. Because then, the central object is not passive wreckage. It is an engine. And once that possibility is taken seriously, the whole supernova has to be reinterpreted from the inside out. A neutron star is already an absurd thing to exist. It carries more mass than the Sun in a sphere only a few tens of kilometers across. Matter inside it is compressed to nuclear density. Gravity at its surface is so intense that escape becomes a negotiation with catastrophe. But even this description is not enough. A magnetar is not just a neutron star. It is a neutron star born with a magnetic field so extreme that the field itself becomes a major actor in the evolution of the system. And in the first moments of its life, it may also be spinning at a rate so violent that the object stores a colossal reservoir of rotational energy. This is the key transition. The obvious explanation is not the explosion. The real explanation may be the compact survivor beneath it. When a massive star's core collapses, angular momentum is forced inward as the core shrinks. The same physical logic that makes a skater spin faster when pulling in their arms becomes brutal at stellar scales. A slowly rotating stellar core can become a neutron star turning in milliseconds. That means hundreds of rotations every second. It means the surface is moving with a speed that begins to feel less like ordinary rotation and more like disaster. A newborn object in this state carries enough rotational energy to rival or exceed the visible energy budget of the supernova around it. But stored energy means nothing unless there is a mechanism to spend it. This is where the magnetic field changes everything. As the magnetar spins its magnetic field, interacts with the surrounding plasma, and launches an outflow of electromagnetic energy and relativistic particles. The star spins down. Rotation is drained. Energy leaves the compact object and is deposited into the expanding ejector. The dead star becomes brighter, not simply because it exploded well, but because the thing created in its center keeps feeding debris from below. Once seen this way, the central engine model becomes more than a clever fix for a light curve. It becomes a change in narrative architecture. A traditional supernova is front-loaded. Most of the meaningful physics happens at the moment of collapse and shock breakout, and the later light is the fading consequence of that initial act. A magnetar-powered supernova is different. It is distributed in time. The collapse matters, but the remnant continues the event. Energy is not only inherited from the blast, it is injected after the blast. This distinction explains why superluminous events can remain so bright for so long without forcing every detail into radioactive decay or an exquisitely tuned external environment. The magnetar acts like a central battery discharging into matter that is still optically thick enough to trap and thermalize a large fraction of that energy. The ejector does not merely cool, it is reheated, inflated, and in some cases reshaped by what sits at the center. That is why the engine model is so compelling. It does not just offer more power, it offers a believable way to deliver that power over time. The timing matters as much as the amount. A magnetar, born spinning rapidly, can dump energy quickly enough to help explain the enormous peak luminosities of superluminous supernovae, while continued spin down can sustain the brightness over longer intervals. If the field is stronger, the braking can be more severe and the energy can be released faster. If the spin is faster, the reservoir grows larger. The observed light curve becomes a visible compromise between rotation, magnetic field strength, ejector mass opacity, diffusion time, and geometry. In other words, the supernova becomes an exposed system, not a single explosion, but a negotiation between central power and outward escape. This also explains why the model is attractive without being trivial. A magnetar is not a magic word. It does not end the argument. It opens a more disciplined one. The field strength cannot be arbitrary. The rotation rate cannot be infinite. The ejector must still behave like real matter, with real opacity and real diffusion delays. The engine has to fit the light, not merely overpower it. That is why events like SN 2024 AFAV are so valuable. They are not just bright enough to suggest a central engine. They are structured enough to pressure the details of that engine. If the compact object is truly governing the light, then the light curve is not just evidence that a magnetar may exist. It becomes evidence about how it loses energy, how its surroundings are configured, and whether additional effects such as asymmetry or fallback complicate the simple spin-down picture. The surface story is stellar death. But now another story is emerging underneath it. A city-sized object forms in the crushed heart of a star. It is born spinning with catastrophic speed. It is threaded by a magnetic field that can strip rotational energy out of it and pour that energy into the wreckage around it. The explosion that should have been ending instead becomes a transfer mechanism. The remnant takes command of the aftermath. The visible brilliance is no longer just the scar left by collapse. It is the ongoing work of the object that survives collapse. This is the deeper truth superluminous supernova keep pointing toward. Their light is not merely what remains after the star dies. Their light may be the first signature of something newly born and violently active inside the ruin. And once the remnant becomes the engine, the next question becomes more dangerous than whether a magnetar exists. It becomes how such an engine couples to matter that is falling, expanding, colliding, and twisting around it. A neutron star does not need to be large to be terrifying. It needs to spin. That is the next inversion in this story, and it matters because size misleads the imagination. A newborn magnetar is not a vast object spread across millions of kilometers, like a swollen star in its dying phase. It is a compact survivor, only tens of kilometers across a city-sized remnant, packed so densely that familiar matter barely remains familiar at all. And yet, in the moments after core collapse, that tiny object can carry enough rotational energy to help govern the fate of the explosion around it. This is the contradiction that makes magnetars so narratively dangerous. The visible supernova is enormous. The engine that may dominate it is microscopic by stellar standards. The story on the surface is bigger than the object underneath. The power underneath is bigger than the story on the surface. The reason is angular momentum. Before collapse, the core of a massive star may rotate at a pace that seems unremarkable on stellar terms. But when that core implodes, its radius collapses by orders of magnitude. The same conserved motion is suddenly confined to an object dramatically smaller. Rotation is compressed. Spin accelerates. A core that once turned leisurely can become a neutron star with a period measured in milliseconds. That means one full rotation in 1,000th of a second. Hundreds of turns every second. In some extreme cases, roughly 1,000. This is not just fast. It is a physical regime in which rotation stops being a property and becomes a resource. A typical neutron star born with a spin period of a few milliseconds can store rotational energy on the order of 10 to the power of 52 ergs, enough to rival the kinetic energy associated with a supernova explosion, and vastly exceed the visible light the event would otherwise radiate. That number is easy to recite and difficult to feel. So, it helps to translate it into consequences. If even part of that reservoir is extracted and delivered into the ejector over the right timescale, the brightness of the explosion can be elevated far beyond what radioactive decay alone could comfortably maintain. The event does not have to be born impossibly luminous. It can be made luminous by continued payment from the center. This is why rotation is not incidental. It is the first treasury. But a treasury is not a mechanism. The energy can exist without being useful unless the star has a way to lose it efficiently. That is why spin by itself is not enough to explain a superluminous supernova. A rapidly rotating neutron star without a sufficiently intense magnetic field is still extraordinary, but it does not necessarily become the kind of engine this story requires. Rotation has to be coupled to torque. The stored energy has to be bled away. The object must be able to break hard enough to matter, while the expanding debris is still dense enough to absorb what is being dumped into it. This is the timing problem at the heart of the magnetar model. Release the energy too slowly, and the ejector becomes too diffuse to trap it efficiently. Release it too fast, and much of the energy may go into acceleration rather than sustained radiative display, or be lost in channels that do not map neatly onto the observed light. The visible brilliance of a superluminous supernova, therefore reflects a compromise between reservoir and release, between how much rotational energy is stored at birth and how violently the newborn object is forced to surrender it. That is why millisecond rotation is so important. It gives the system room to work, it makes the central engine credible, and it reveals something else that is easy to miss. The death of the star is not only creating a remnant, it is concentrating history. The angular momentum of a stellar core accumulated over a long life of burning and transport and internal struggle is suddenly compressed into a tiny object that can spend that inherited motion in days, weeks, or months. A long stellar past is converted into a short, violent future. This is one of the reasons the Magnetar hypothesis is more than a numerical convenience. It feels structurally right for the phenomenon it is trying to explain. Superluminous supernovae are not just bright. They are bright with a kind of controlled excess, as though a hidden cache of ordered energy is being spent inside chaos. Rotation is exactly that orderly motion available for catastrophic conversion. And once this possibility is admitted, another layer of the event becomes visible. A newborn magnetar is not merely spinning quickly in empty space. It is embedded inside expanding ejecta, enveloped by plasma, threaded by intense fields, and in some cases surrounded by material that failed to escape cleanly in the explosion. In that environment, spin is never just spin. It interacts, it twists, it launches winds, it drives shocks. It can inflate a high-energy bubble beneath the ejecta and alter the way radiation diffuses outward. The compact object does not simply sit at the center like a flywheel. It becomes a forcing function inside a violently changing medium. This is the point at which rotation becomes catastrophe in the most useful sense of the word. The newborn remnant is born too fast for calm evolution. It has to shed energy. It has to break. And that breaking is not a quiet correction. It is one of the central acts of the supernova itself. The easy picture says the explosion happens once. The deeper picture says the explosion keeps being reorganized by what the central object is trying to become. A rapidly spinning neutron star cannot remain in that newborn state for long. It must spin down. It must pay out. It must transform rotational order into electromagnetic and particle outflow. The real problem is not whether such an object can exist. The real problem is how the universe grips that rotation tightly enough to turn a city-sized remnant into a power source visible from a billion light-years away. And that is where spin alone gives way to something harsher, stranger, and far more controlling than rotation itself, the magnetic field. Rotation gives the magnetar a fortune. The magnetic field decides how brutally that fortune is spent. That is the next turn in the descent, and it matters because speed alone does not explain a superluminous supernova. A millisecond neutron star can hold enormous rotational energy, but stored energy is only potential. To make the explosion around it brighter, stranger, and longer-lived, that energy has to be extracted, directed, and forced into the ejecta on exactly the kind of timescale that the visible light demands. The magnetic field is the instrument of that extraction. And in a true magnetar, it is not merely strong. It is so extreme that ordinary stellar language starts to feel decorative rather than descriptive. Earth has a magnetic field that guides compasses and deflects charged particles from the sun. The sun has a field powerful enough to drive flares and shape the solar wind. A magnetar is born with a dipole field that can reach around 10 to the power of 14 to 10 to the power of 15 Gauss, roughly 1 trillion times stronger than Earth's surface field. intense enough that the field stops being a feature of the star and becomes part of the star's fate. This is why the name matters. Magnetar does not simply mean neutron star with more magnetism than usual. It means an object in which magnetism becomes one of the dominant organizing forces of the system. The obvious explanation is that the field just makes the star exotic. The real explanation is harsher. The field is what allows rotation to become luminosity. As the newborn object spins, its magnetic axis may not align perfectly with its rotation axis. That misalignment matters. A rotating magnetic dipole radiates. The star loses rotational energy through electromagnetic torque and a wind of relativistic particles and fields. In plain terms, the magnetar breaks itself. But this breaking is not a quiet slowing. It is the method by which the central engine dumps power into its surroundings. The stronger the field, the more effectively it can tap the rotational reservoir. The shorter the spin period, the larger the reservoir available to tap. Those two quantities together begin to define the entire event. If the field is too weak, the engine releases its power too slowly to explain the brightest superluminous peaks. If the field is too strong, the energy can be dumped too abruptly, or alter the dynamics in ways the observed light does not support. The light curve becomes a visible negotiation between spin and magnetism, not just between explosion and debris. This is one reason the recent interpretation of SN 2024 AFAV is so striking. The bumps in its light do not merely suggest that a magnetar exists. They appear consistent with a central engine whose spin period and field strength can be independently constrained by the overall light curve and the changing spacing of the bumps. That changes the role of the magnetic field from abstraction to measurement. It is no longer just something theorists invoke because the numbers look convenient. It becomes part of the geometry and timing written into the event itself. But the field does more than break rotation. It also reshapes the immediate environment of the newborn neutron star. The collapsing core is not born into emptiness. It is embedded in a furnace of plasma neutrinos, turbulence, radiation, and debris that is still deciding whether it escapes, falls back fragments, or couples to the central outflow. In that environment, a magnetic field of magnetar strength can launch winds, inflate a hot nebula behind the ejector influence, how energy thermalizes and affect which channels remain open for matter and radiation. The remnant is not just losing energy, it is imposing structure. This is why the field has to be understood not as a label, but as a machine. It talks, it channels, it redirects. It changes the pressure distribution around the central object. It may help support or disrupt nearby material. It may determine whether fallback matter can approach cleanly or is forced into a more complicated arrangement. In a superluminous supernova, the magnetic field is not an ornament on the remnant. It is the means by which the remnant reaches back into the explosion and keeps rewriting it after the initial blast. That realization also makes the birth of the field itself part of the drama. Magnetars are not assumed simply because neutron stars are dense. The required fields likely emerge from violent amplification during or immediately after collapse in a proto-neutron star, where differential rotation and convective dynamo action can drive magnetism to astonishing strength if the newborn object is rotating fast enough. That is another hidden cost in the story. To get a field this strong, the birth conditions themselves must already be extreme. Rapid rotation does not merely provide the reservoir. It may also help build the very mechanism that empties the reservoir. The engine is born entangled with its own brake. And once that is true, the supernova no longer looks like a singular event. It looks like a self-coupled system with feedback built into its origin. The star dies. A neutron star forms. The neutron star spins rapidly enough to store a vast amount of ordered energy. That rapid rotation helps sustain magnetic amplification to Magnetar's strength. The magnetic field then strips away the spin energy and feeds it back into the ejector. The remnant spends its birth conditions into the very explosion that conceals it. That is the deeper architecture now emerging from these events. What appears from a distance to be one overpowered blast is at closer range a compact object discharging itself into the ruins of its parent star. And the magnetic field is the discipline that makes the discharge visible. Yet even this is not the full story. A strong field can extract energy. It can torque the star. It can shape outflows and pressure. But SN 2024 AFAV does not merely show excess brightness. It shows patterned irregularity, a chirped sequence in which the spacing of the bumps changes over time. That kind of structure hints at something more than simple dipole spin-down. It suggests that the field is acting in a system where geometry matters, where nearby matter may be tilted in falling and dynamically coupled to the central engine. In other words, the field may not just be draining the magnetar. It may be governing an interaction with something that should not have survived so close to the object at all. Relativity is supposed to live far away from ordinary life, somewhere near black holes, gravitational waves, or clocks on satellites. It is not supposed to arrive in the middle of a dying star's light curve and start rearranging the meaning of the explosion. Yet this is exactly the deeper turn forced by events like SN 2024 AFAV. Because once a newborn magnetar is admitted as the central engine, and once the brightness begins to show structured bumps instead of a smooth decline. The next question is no longer only how much energy is being released, it is how that release is being modulated. A reservoir of rotational energy can explain excess light. A strong magnetic field can explain why that reservoir is drained. But a patterned sequence of changing intervals hints at something else. It hints at geometry. It hints at motion that is not random. It hints that the central engine may not simply be spinning down in isolation, but interacting with nearby matter in a way that changes orientation over time. And that is where Einstein enters the room, not as decoration, as mechanics. The specific effect at issue is frame dragging, often called lens-thirring precession, one of general relativity's stranger promises. A sufficiently massive rotating object does not merely sit in space-time. It twists the space-time around it. The faster it spins and the more compact it is, the more severe that twisting becomes near the object itself. In everyday situations, this effect is tiny. Around a newborn neutron star spinning in milliseconds, compressed to a city-sized body with gravity just short of black hole collapse, it can become dynamically relevant for matter trying to orbit nearby. This only looks abstract from a distance. Up close, it means that space and time are not passive scenery around the remnant. They begin to participate in the event. If a disk of fallback material forms around the newborn magnetar, and that disk is tilted relative to the star's spin axis, then the dragged spacetime can force the disk to precess, not explode, not immediately vanish. Precess. Its orientation slowly changes like the wobble of a spinning top, except here the top is a ring of stellar debris circling one of the densest objects in the universe, while space-time itself is being pulled around by rotation. That motion matters because the disk is not just an inert structure. It can regulate inflow, alter how outflows are shaped, change the direction and efficiency of energy deposition, and periodically modify what the outside universe is able to see. In other words, precession is one of the few mechanisms capable of turning buried central dynamics into a visible rhythm. This is why the interpretation of chirped bumps in a superluminous supernova is so provocative. The word chirp usually evokes gravitational waves, a signal that rises in frequency as two compact objects spiral together. Here, it means something different, a sequence of brightness modulations whose spacing changes with time. The pattern does not stay fixed, it tightens. That matters because a fixed period could come from many repetitive nuisances in the data or from a simple orbital or rotational clock. A changing period suggests evolution in the system itself. It suggests that the structure responsible for the modulation is moving inward, changing its coupling or precessing, faster as conditions evolve. A fallback disk under lens-thirring precession offers exactly that kind of behavior. As material accretes, redistributes angular momentum, and migrates, the characteristic precession timescale can shorten. The bumps in the light curve would then not merely mark brightness fluctuations. They would become visible timestamps of changing motion in strongly curved spacetime. That is the real escalation here. The supernova would no longer just tell us that a compact object exists. It would tell us that the orientation and relativistic environment of matter near that object are changing in ways we can infer from light a billion years after it was emitted. The achievement is real. The cost is larger. Because invoking frame dragging is not a casual move. It means the easy explanations have already begun to fail. Radioactive decay does not give you a chirped sequence of bumps. A generic bright explosion does not naturally encode evolving relativistic geometry into its luminous history. Even an ordinary Magnetar spin-down model, powerful as it is, tends to produce a smoother energy injection unless something nearby is shaping or redirecting the way that energy reaches the ejector. Relativity enters the story only because simpler frameworks begin to run out of explanatory leverage. And once it enters, the event grows stranger again. A star dies. A neutron star is born. The neutron star spins rapidly enough to drag local spacetime. Material that failed to escape the explosion falls back and settles into a tilted disk. That disk is forced into precession by the twisted geometry around the remnant. The precession modulates how energy is supplied or expressed through the expanding ejector. The light curve records the changing intervals of that precession as chirped bumps. What looked from far away like a bright stellar death now begins to resemble a compact laboratory for general relativity. Accretion physics and magnetic spin-down all operating at once. This is why the birth of a magnetar in real time is such a destabilizing idea. The object is not only extreme, it is born into a system where multiple forms of extreme physics become visible together. Collapse physics creates the remnant. Rotation provides the reservoir. Magnetism extracts the power. Fallback supplies nearby matter. Relativity twists the stage on which that matter moves, and the light escaping the debris becomes the messenger broad enough to carry the combined result across intergalactic distance. The surface story keeps shrinking. The deeper story keeps widening. By the time Einstein appears, the supernova is no longer just an explosion with extra brightness. It is a coupled engine in which time, motion, curvature, and debris are all negotiating in the open. But relativity is still not the final answer. Frame dragging can explain how orientation changes become periodic and why those periods may evolve. It does not explain why there is nearby matter to precess in the first place. For that, the story has to move from twisted space-time to the debris that should have escaped, and yet somehow comes back. An explosion is supposed to separate. That is one of its defining moral claims. Matter is blown outward, debris escapes, the old structure is shattered, and whatever survives at the center is left behind, while the rest of the star is cast into space. Fallback violates that logic. It is the return of matter that should have been gone. It is the refusal of the wreckage to stay wreckage. And once that return begins, the entire architecture of the supernova changes again. Because the central engine is no longer interacting only with expanding ejecta at great distance. It now has to contend with material that loses the argument with gravity, turns around, and comes back toward the newborn Magnetar. This is the deeper scandal inside a system like SN 2024 AFAV. The star explodes. The remnant forms. The debris races outward. But not all of it escapes cleanly. Some fraction remains only marginally unbound, slowed by reverse shocks, asymmetries, incomplete energy transfer, or the simple fact that the inner ejecta still lives close to the gravitational edge. That material does not disappear into the background, it falls back. And fallback is not a cosmetic detail. It is a second catastrophe hidden inside the first. In ordinary language, one might imagine this returning matter raining straight down onto the compact object. Reality is crueler and more interesting. In a rotating system, infalling matter usually carries angular momentum. However damaged and chaotic the star has become, the debris still remembers motion. As it returns inward, it cannot simply plunge radially all the way to the center unless that angular momentum is somehow erased. Instead, much of it circularizes. It spreads. It forms a disk. This is the object that should not survive so close to such violence, and yet may be essential to understanding the violence itself, a fallback accretion disk around a newborn Magnetar. The phrase sounds technical. The consequences are anything but. Once a disk exists, the supernova is no longer just a Magnetar losing rotational energy into expanding debris. It becomes a coupled engine. The remnant spins, the magnetic field torques, the ejecta expands, and a reservoir of returning matter begins to orbit in the middle of it all. That disk can feed the Magnetar. It can alter the field geometry near the star. It can modulate outflows. It can bury magnetic flux temporarily or interact with it violently. It can change how energy escapes where it is deposited and on what timescale the outside universe sees the result. What looked from far away like a single luminous blast becomes at closer range an ecosystem of feedbacks trapped inside debris, moving thousands of kilometers per second. This is why fallback matters so much in the interpretation of SN 2024 AFAV. The chirped modulations are not easily explained by a Magnetar spinning down in perfect isolation. Some nearby structure must help translate central dynamics into visible rhythm. A misaligned fallback disk provides exactly that missing structure. It is matter close enough to the engine to feel the twisted space-time around it. It is matter persistent enough to evolve over weeks and months. And it is matter asymmetric enough to create changing observational consequences rather than a smooth, featureless glow. The obvious explanation is that the disk is just leftover clutter. The real explanation is that the disk may be the interface between hidden engine physics and the light curve we actually observe. That is a much larger role, and it brings with it a set of uncomfortable implications. First, the explosion that produced the supernova was not as clean as the surface brightness suggests. Something remained bound or nearly bound. Second, the newborn magnetar is not simply surrounded by an empty cavity inflating under its own wind. It is born into continuing negotiation with stellar debris that has unfinished business with gravity. Third, the timescale of the event is extended, not only because the magnetar keeps paying out rotational energy, but because the surrounding environment near the engine is still rearranging itself after the formal moment of stellar death. A fallback disk is therefore not just an accessory to the model. It is evidence that collapse does not resolve into aftermath as quickly as the word explosion encourages us to think. It is also why this stage of the story begins to resemble accretion physics more familiar from black holes, X-ray binaries, or active galactic nuclei, except under conditions even less forgiving. Here, the central object is not a mature compact remnant in a settled environment. It is a newborn magnetar, still spending the energy of its birth, wrapped in expanding ejecta, perhaps contending with intense neutrino history. Magnetized wind shocks and matter that is both returning and redistributing angular momentum at the same time. The disk that forms in such an environment is unlikely to be calm, thin, or symmetrical in the way textbook sketches encourage. It is likely hot evolving, magnetized, and vulnerable to warping or tilt. That vulnerability is precisely what makes it useful. Because once the disk is misaligned relative to the magnetar's spin axis, the stage is set for precession, and once precession begins, the changing geometry can modulate what the outer ejecta receives, or what distant observers infer from the escaping light. The light curve then stops being merely a record of power. It becomes a record of orientation. That is a profound shift. We are no longer asking only how much energy the engine supplies. We are asking how the engine and nearby matter move relative to each other while buried inside an exploding star. This is what makes fallback feel almost insulting to the old picture of stellar death. The blast is not enough. The remnant is not enough. Even the magnetic braking of a newborn magnetar is not enough by itself. The universe adds one more layer debris that returns, remembers its angular momentum, and settles into a disk precisely where the system is most dangerous and least observable. It is a hidden structure with disproportionate power over what the event becomes. And because it is hidden, the only way to find it is through the distortions it leaves in the light. That is the deeper truth now emerging. Fallback is not failure of escape. It is persistence of influence. It is the way the dead star reaches back toward the object born from its own collapse and keeps participating in the story after its destruction should have been complete. Yet, a disk alone does not guarantee visible structure. Matter can orbit quietly for a while and still tell us very little. What matters next is that this disk is unlikely to be perfectly aligned, perfectly symmetric, or perfectly stable. It is precisely its tilt, asymmetry, and evolving motion that may turn a buried engine into a signal that flickers, tightens, and begins to sound like a chirp. Fallback does not simply complicate the magnetar. It can change what the magnetar becomes. That is the next escalation, and it matters, because a returning disk of stellar debris is not just a witness to the birth of the remnant. It is a participant in that birth. Once matter turns around and begins falling back toward the newborn neutron star, the story stops being one of a central engine operating in a passive environment and becomes one of mutual interference. The magnetar is trying to shed rotational energy through its magnetic field. The fallback material is trying to settle spiral inward and redistribute angular momentum under conditions of almost absurd violence. The ejecta above them is still expanding. The optical display far away still looks like a supernova. But down near the center, beneath layers of debris and diffusion and glare, the event has become more unstable than the surface light admits. This is why fallback should be understood as a second catastrophe rather than a leftover detail. It does not merely add mass near the remnant. It introduces leverage. Matter returning to a newborn magnetar can in principle do several things at once. It can feed accretion onto the compact object and alter the local pressure balance. It can interact with the magnetic field in ways that change how efficiently rotational energy is extracted. It can partially bury or distort the external dipole field if enough material is forced inward, modifying the star's torque and changing the apparent spin-down behavior seen from the outside. It can help collimate outflows or disrupt them. It can act as an absorbing scattering or reprocessing structure through which central power must pass before it reaches the expanding ejector. And because fallback is not a one-time act, but an evolving flow, all of these effects can change with time. That last point is the real danger. A static complication would be annoying. An evolving complication can write itself into the light curve. This is why the chirped structure in SN 2024 AFAV matters so much. A smooth Magnetar spin-down model already provides a plausible global power source for superluminous supernova. But the changing brightness bumps imply that something near the engine is not simply present. It is active, asymmetric, and evolving. A fallback disk supplies all three. It is active because matter continues to move, collide, and migrate inward. It is asymmetric because a disk tilted relative to the spin axis of the magnetar cannot help but create directional consequences. It is evolving because accretion redistributes mass and angular momentum, changing the structure and behavior of the disk over time. Once that is true, the disk is no longer just a geometric object that precesses and occasionally modulates the light. It becomes a control surface for the entire event. The obvious explanation is that the magnetar powers the supernova and the disk adds a wobble. The real explanation may be harsher. The magnetar and the disk may be locked in an ongoing struggle over how the magnetar's birth energy is allowed to escape. In one direction, the magnetic field can push back on inflowing matter, truncate the inner disk, and force accretion to proceed through unstable channels. In the other direction, the returning matter can load the field lines, alter the magnetosphere, and change how cleanly the star behaves as an isolated rotating dipole. The result is not neat. It is a changing central engine whose observational signature depends on both what the magnetar is doing and what the surrounding disk permits it to do. This also means the light curve is carrying more than luminosity information. It is carrying negotiation. Every bump may represent a moment when the balance between injection, reprocessing geometry, and obstruction shifts enough to become visible across a billion light-years. The supernova does not merely glow, it argues with itself. That is why fallback is such a powerful idea in this context. It explains how the event can be both globally powered by a magnetar and locally modulated by nearby matter without needing to abandon the central engine framework. More importantly, it reveals that the birth of a magnetar may not be a clean transition from collapse to stable remnant. It may instead involve a turbulent period in which the newborn object is still fighting over its surroundings, its field structure, and the terms under which its rotational energy can be spent. In that sense, fallback is not a postscript to the explosion. It is part of the mechanism by which the compact object emerges into the observable universe. The dead star is still shaping the newborn neutron star long after the formal moment of death has passed. The returning material may decide how visible the engine is, how orderly its output appears, and how rapidly its central properties can be inferred from the light above it. That is a much larger role than debris is usually allowed to have. It also widens the meaning of the event. Stellar death is often imagined as a hierarchy. First collapse, then explosion, then remnant. Fallback destroys that clean sequence. Collapse creates the remnant, yes. Explosion launches the debris, yes. But some of the debris returns and begins influencing the remnant while the remnant is still influencing the debris. Cause and aftermath fold back into one another. The explosion is no longer something that happened and then ended. It is a system that keeps revising itself from the center outward. And because that revision is happening in the most relativistic, magnetized, least directly visible part of the event, the only way to catch it is through the timing, spacing, and shape of the light. That is why fallback becomes a second catastrophe. The first catastrophe makes the magnetar. The second determines how that magnetar is allowed to announce itself. And once the light begins to carry that hidden struggle in a patterned way, the supernova stops looking like a single blast with extra brightness and starts looking like a message from a buried machine whose rhythm can finally be read. For most of human history, the sky only offered two forms of stellar truth. There were stars that persisted, and there were stars that changed. Modern astronomy has made that distinction far more exacting. Now, a changing point of light can be turned into a history of pressure, opacity, expansion, geometry, and hidden engines. A light curve is not just a graph. It is the closest thing astrophysics has to a confession extracted from an object too distant to touch. And when that confession begins to stutter, hesitate, or repeat with changing rhythm, the event stops looking simple, no matter how spectacular its brightness may be. That is where SN 2024 AFAV becomes especially dangerous to the old story. Because a supernova can be extremely bright and still remain conceptually manageable if it fades in a smooth, disciplined way. The blast happens. Radiation diffuses outward. The ejector expands and cools. The curve rises and falls. But when the brightness develops, shoulders, humps, and structured deviations from a clean decline, the light stops behaving like the residue of one catastrophe and starts behaving like the visible surface of an ongoing process. This is the difference between a fireball and a system. A fireball spends what it has. A system modulates what it spends. That is why the light curve matters more than the headline luminosity. Brightness tells you scale. Structure tells you causality. In ordinary supernova language, the broad shape of the light curve is governed by a fairly intuitive tension between energy input and energy escape. The explosion injects energy. Radioactive decay may continue to contribute. The ejector remains opaque for a time, trapping radiation until it diffuses out. As the material expands, density drops, opacity changes, and the light declines. The curve may be rich, but it is not usually mischievous. It has memory of initial conditions, not constant revision from a buried engine. That expectation is what events like SN 2024A FAV begin to undermine. Its luminosity alone already pressures familiar explanations. Its internal pattern does something more profound. It implies that the event is not only luminous but articulate. Something in the system is imprinting timing onto the escaping light. Something is making the brightness fluctuate in a way that is too organized to ignore and too evolving to treat as noise. This is why the humps matter. A single secondary bump in a supernova can sometimes be explained through multiple paths. Shock interaction with circumstellar material can briefly revive the light. Cooling structure in the ejector can produce a shoulder. Changes in ionization or diffusion can create subtler distortions. But repeated quasi-periodic modulations with changing intervals create a different kind of pressure. They suggest a clock. More importantly, they suggest a clock that is itself changing. That is the crucial distinction. Fixed repetition can come from many simple systems. A changing cadence implies that the underlying geometry radius, inflow, or coupling is evolving while the event is still underway. The accepted explanation is not just incomplete here. It begins to look like the wrong category of explanation. Because once the light curve starts speaking in pattern rather than merely in magnitude, the question is no longer only what powers the event. The question becomes what organizes the power. That is a much harder problem. Radioactive nickel can sustain light. It does not usually create chirped structure. A one-time blast can leave behind cooling debris. It does not naturally tighten intervals over time. Even a clean Magnetar spin-down model powerful enough to explain prolonged luminosity tends by itself towards smoother global behavior. To get patterned irregularity, especially changing irregularity, the engine has to interact with something. Nearby matter, geometry, precession, obstruction, reprocessing, differential injection. The visible brightness then becomes less like the reading on a fuel gauge and more like the output of a machine whose moving parts are briefly exposed through noise opacity and distance. This is why the light curve of SN 2024 AFAV feels so consequential. It does not merely support the idea of a central engine. It begins to reveal the behavior of that engine through time. The bumps are not just decorations on the luminosity profile. They are clues about the hidden arrangement of the central system. Their spacing hints at a process with memory. Their changing spacing hints at a process whose characteristic timescale is shrinking or whose orientation is evolving. Their persistence hints that this process is not occurring once, but repeatedly as the ejector continues to expand and the central engine continues to interact with its surroundings. In that sense, the light curve becomes the only direct witness available to the most inaccessible region of the event. We cannot see the newborn Magnetar itself. We cannot image the fallback disk. We cannot watch space-time being twisted around the remnant. But we can watch the light arrive in a sequence that preserves the consequences of all of those hidden conditions. The event, in effect, tells on itself. That is what makes modern time-domain astronomy so powerful and so unsettling. We do not simply discover transient explosions anymore. We interrogate them. We measure them night after night, ask how fast they change, ask whether they return to previous states, ask whether the intervals between deviations stretch or contract, ask whether color and temperature shift in step with luminosity or resist it. A supernova once seemed like an object. Increasingly, it behaves like a conversation conducted through time. And some conversations are far more revealing than a single image could ever be. This is the deeper transformation underway in the story of Magnetar birth. A brilliant explosion alone could still be forced into familiar categories. A structured light curve resists that flattening. It makes the event legible as a coupled system. The star has died, yes. But the remnant is still acting nearby. Matter is still moving. Energy is still being redirected. And the outer debris is still translating that buried struggle into observable light. The humps, therefore, are not interruptions to the story. They are the story becoming readable. They are the moment when the brightness stops being spectacle and starts becoming evidence. And once evidence begins to carry rhythm, the next question becomes unavoidable. If the light really is tracing a clock deep inside the explosion, then the extraordinary claim is no longer just that a magnetar exists in the wreckage. It is that astronomers may be watching its birth unfold while the engine is still learning how to behave. Birth is usually the part the universe hides. That is the first truth that makes this claim so extraordinary. Astronomers are used to seeing aftermath. They see supernova remnants centuries after the explosion has passed. They see pulsars long after their natal chaos has settled into regularity. They see magnetars as already existing objects, their violence inferred from bursts. Flares spin periods and magnetic power that survive after the original catastrophe is gone. But to catch the birth of such an object in real time is a different category of event entirely. It means seeing not just the survivor, but the conditions under which survival begins to control the destruction that created it. It means the remnant is not inferred from a static corpse of gas long after the fact. It is inferred while the explosion is still alive, still bright, still changing, still arguing with itself in public. That is why SN 2024A FAV matters beyond the mechanics of any one model. The deeper significance is temporal. The evidence does not arrive from archaeological reconstruction. It arrives during the event. And that changes the standard of what it means to witness a compact object being born. There is an important distinction here. Astronomers have long believed that some superluminous supernovae are powered by newborn magnetars. The idea is not new. The intellectual groundwork has been in place for years. The difficulty was never that the concept lacked elegance. The difficulty was that nature kept offering brightness without confession. A very luminous explosion can support multiple interpretations. A broad light curve can be fit by competing mechanisms if enough freedom is allowed in the environment, ejector, and central parameters. Inference remained possible. Certainty remained slippery. That is the normal condition of high-energy astrophysics. The signal arrives incomplete, and the universe forces patience. What makes an event feel like a real-time birth, then, is not that a telescope somehow photographs a magnetar coming into existence. No instrument sees the compact object directly inside the ejector. The claim is subtler and more demanding than that. It is that the evolving light from the system begins to behave in a way that is most naturally explained by the remnant itself, actively shaping the event while the event is still underway. The birth is not seen as an image. It is seen as control. That is a much stronger statement than simple survival. A neutron star might form in many supernovae and remain observationally silent beneath the debris. Here, the possible remnant does not remain silent. It appears to intervene. Its rotational energy magnetic field nearby fallback matter and perhaps relativistic precession begin to leave fingerprints on the observable evolution of the explosion before the system has had time to settle into anything calm. That is why the phrase real-time matters so much. Not because the event happens quickly on human timescales, although it does evolve over months rather than millennia, but because the interpretation is being extracted from a transient system during the window in which its central machinery is still exposed through behavior. There is no comfort of hindsight here. There is no ancient remnant whose structure can be mapped at leisure. No clean pulsar timing solution matured over decades. No quiet nebula in which the central engine has already become a known quantity. Instead, there is a brilliant, unstable supernova whose light has to be monitored night after night, while theories compete to explain what the system is doing. The achievement is real. The risk is built into it. To claim a birth caught in real time is to accept that one is reasoning under active conditions while the evidence is still unfolding. That is what makes the moment scientifically powerful and psychologically tense. Time-domain astronomy has changed the field precisely because it makes such moments possible. Wide-field surveys scan the sky repeatedly, discovering transients not as isolated curiosities, but as evolving events with histories that can be measured. Follow-up campaigns then turn brightness into cadence, cadence into structure, into model pressure. A supernova is no longer just discovered. It is watched. Its color changes spectral features. Rise, time, decline, rate, temperature, evolution, and deviations from smooth behavior all become part of the same interrogation. In the case of SN 2024A FAV, that sustained attention is what allows the deeper claim even to exist. Without repeated monitoring, the event might simply have joined the catalogue of very bright explosions and remained another suggestive example in favor of Magnetar engines. With careful, time-resolved observation, it becomes something more troubling and more revealing, a system whose luminosity and internal modulation together point toward an engine in the act of establishing itself. This is also what separates the event from a purely theoretical demonstration. The model is not being proposed in empty space. It is being forced by a specific luminous history. A superluminous supernova is seen. Its brightness already challenges ordinary power sources. Its light curve then develops structured, changing modulations. Those modulations point toward a tilted fallback disk under relativistic precession around a rapidly spinning newborn compact object. The global energy budget points toward Magnetar spin-down. Step by step, the visible behavior narrows the explanatory path until the central remnant ceases to be a speculative leftover and starts to look like the main actor. That narrowing is what gives the phrase "caught in real time" its force. The universe is not merely allowing us to imagine the birth of a magnetar. It is constraining us toward it while the supernova is still bright enough to matter. Yet this is exactly why caution becomes inseparable from excitement, because real-time inference is still inference. A compelling model is not the same thing as a direct unveiling. The story may be converging, but it is converging under uncertainty, with competing explanations weakened rather than annihilated. That tension is not a flaw in the event. It is part of what makes it scientifically mature. The claim is strongest precisely because it has to survive active scrutiny instead of resting on retrospective storytelling. And that is the larger transformation now underway. Astronomers are no longer satisfied to say that some explosions probably leave exotic remnants behind. Increasingly, they can watch the remnant seize command of the explosion and force its properties into the escaping light. The birth of a magnetar, if that is what SN 2024 AFAV is showing, is not a hidden fact buried under debris forever. It is a process becoming legible while the debris still glows. But this also means the burden of proof grows heavier, not lighter. The brighter and stranger the claim becomes, the more ruthlessly every easier explanation has to be tested and made to fail. The story is now too large for the old language that first seemed sufficient. A star collapses. A supernova explodes. A remnant is left behind. That sequence still contains truth, but only in the thin way that a map contains a continent. It preserves order while losing structure. What SN 2024A, FAV, and events like it begin to force instead is a more dangerous picture, one in which stellar death is not a terminal act followed by passive debris, but a prolonged and internally contested transition in which the object born from collapse may become more important than the collapse itself. That is the true reframing now coming into view. The explosion is not the whole story. It may not even be the dominant story once the deepest energy source begins to act. This changes the emotional architecture of supernova physics. For generations, the supernova has been understood as a culminating release, the final catastrophic moment when a massive star's internal struggle with gravity ends in visible ruin. The remnant, whether neutron star or black hole, often enters as a consequence. Important, yes. Sometimes decisive for future astrophysics, yes. But still conceptually downstream. A Magnetar-powered superluminous supernova reverses that hierarchy. The remnant is no longer a leftover. It becomes the central engine, the object, whose rotational energy, magnetic field, and interaction with nearby fallback matter help determine the observable life of the event long after the initial collapse has passed. In other words, the death of the star may be less like an ending than like the ignition of a new physical regime. This is why the phrase stellar death starts to become misleading. Death suggests cessation. The deeper truth here is conversion. A large, diffuse as long-lived star gives way to a tiny, dense, short timescale engine capable of dominating the brightness of the wreckage around it. Ordered rotation, inherited from the stellar core, is compressed into millisecond spin. Magnetic amplification transforms that spin into extractable power. Debris that fails to escape returns as fallback and may settle into a disk, creating feedback between remnant and ejector. Relativity enters because the remnant is compact and rapidly rotating enough to drag local spacetime. The visible supernova becomes the translation layer through which all of this hidden physics leaks into view. Once seen this way, the event is no longer primarily about a blast wave. It is about a transfer of agency from star to remnant. The star dies, the remnant takes over. That single shift rewrites the meaning of the light. Brightness is no longer just what the explosion had at the beginning. It is what the central engine continues to do afterward. Structure in the light curve is no longer an incidental irregularity in cooling debris. It is the trace of system-level dynamics near the newborn object. Even duration changes meaning. A long-lived luminous display is not simply the slow fading of a huge fire. It may be the outward expression of a compact machine discharging itself into matter that is still opaque enough to make that discharge visible. This reframing has consequences well beyond one event. If some superluminous supernova are indeed powered by newborn magnetars, then stellar death is not a single category with brighter and dimmer examples. It becomes a branching landscape in which the fate of the collapsing core, the angular momentum retained, the magnetic field generated, and the behavior of fallback all determine what kind of visible event the universe produces. Two massive stars may die, and from a distance, both may seem to end in supernovae. But underneath that surface similarity, the physical logic can diverge radically. One explosion may be largely governed by radioactive decay and ejector diffusion. Another may be commandeered by a rapidly spinning neutron star. Another may slip into black hole formation so quickly that the luminous display is cut short or rechanneled through other processes. What used to look like a single broad phenomenon starts breaking apart into hidden subtypes, defined not only by what explodes, but by what survives and how that survivor interacts with the wreckage. This is the larger truth that makes the first birth of a magnetar caught in real time feel so consequential. It is not just a breakthrough about one exotic remnant. It is a challenge to the default grammar of stellar collapse. It tells us that the most visible part of the event may not be the first catastrophe, but the prolonged negotiation that follows it. It tells us that a supernova can remain dynamically alive from the center outward long after the initial shock has done its work. It tells us that the compact object often hidden beneath the language of aftermath may deserve to be moved to the front of the narrative. Even the idea of observation begins to shift under this pressure. To study a supernova is no longer just to measure the explosion and infer the progenitor. It becomes a way of probing the newborn remnant indirectly through luminosity, timing color evolution, and structured departures from smooth decline. The outer debris acts like both shield and messenger. It conceals the central engine physically while revealing it behaviorally. The engine cannot be seen directly, but it can be recognized by the discipline it imposes on the light. That means some of the most important objects in the universe may first become knowable, not through direct detection, but through the distortions they create in systems still trying to hide them. A Magnetar birth is therefore not only a story about extreme physics. It is a story about delayed visibility. The object is born in secrecy and announces itself by taking control. Yet this reframing brings a harder edge with it. The more the remnant becomes the center of the story, the less comfortable the event becomes as a clean example of anything. Because once stellar death is understood as an ongoing system, rather than a completed explosion, every assumption about causal order becomes more fragile. Was the brightness set by the initial blast, or by spin down, or by fallback, or by the changing geometry of a precessing disk? Did the magnetic field merely extract energy, or did it help shape the conditions that made the field observable? Is the light curve recording? The remnant itself, the environment around it, or the argument between them? The old story was simpler because it ended early. The new story is more truthful because it does not. And that is precisely why the next layer becomes unavoidable. A reframed story is not a finished one. It still has to face its limits, its ambiguities, and the possibility that nature is offering not a solved case, but the first clear opening into a class of events whose deeper costs and unresolved pressures are only beginning to appear. The first danger in a breakthrough is that it feels like an ending. A long-standing theory appears to find its smoking gun, the data line up the hidden engine steps into view, and the temptation is to speak as though the case has closed. But nature is usually least forgiving at exactly that moment. Because the more dramatic the claim, the more ruthlessly it has to survive its own success. To say that astronomers may have caught the birth of a magnetar in real time is not just to announce a discovery. It is to accept a heavier burden of proof than the older, looser language ever required. And that burden is part of the story. It is not a bureaucratic afterthought to be added after the excitement. It is the cost of turning an elegant idea into a physical claim about the universe. The evidence for SN 2024A FAV is powerful precisely because it is layered. The global energy budget points toward a Magnetar engine. The chirped modulations point toward a tilted fallback disk whose changing precession can imprint a shrinking timescale on the light. The combined model explains both the broad luminosity evolution and the internal structure better than the simpler alternatives on the table. The authors go further than saying the fit is merely suggestive. They argue that lens-thirring precession is the most plausible explanation for the signal that circumstellar interaction would require extensive fine-tuning to imitate the observed decaying period and smooth sinusoidal residuals, and that lower-level circumstellar effects are not excluded, even if they are unlikely to be the main cause. That is strong. It is also not the same thing as omniscience. This distinction matters because astronomy almost never grants direct access to the systems it cares about most. No one sees the magnetar itself inside the ejector. No one photographs the fallback disk. No one watches space-time twist around the remnant, the way one watches water swirl down a drain. Everything is inferred through light spectra cadence, model comparison, and the stubborn refusal of simpler explanations to reproduce the full behavior of the event. That is real evidence. It is just evidence of a kind that lives and dies by whether the interpretation continues to outperform every competitor as more cases are found. This is why the phrase definitive evidence has to be handled with discipline. It can mean that the current explanation is by far the best supported. It cannot honestly mean that the universe is now forbidden from producing some rarer imposter mechanism that has not yet been imagined. The real problem is not that the model may be wrong in every detail. The deeper problem is that the model may be right in its architecture and still incomplete in its mechanics. A fallback disk may precess. The magnetar may spin down. Frame dragging may organize the chirped signal. And yet, the actual system could still contain lower-level circumstellar interaction, ejector asymmetry, radiative transfer effects, or magnetic complications that the clean version of the model only approximates. In other words, success here is probably not a final picture. It is a narrowing corridor. That is how mature science usually advances. Not by leaping from ignorance to completion, but by making the surviving explanations fewer, harder, and more specific. SN 2024A FAV narrows the corridor dramatically. It does not abolish uncertainty as a category. The paper itself is clearest at exactly this point. It argues that the standard magnetar model alone predicts a smooth monotonic decline and fails to explain the chirped behavior, while the combined magnetar plus lens-Thirring framework fits both the overall light curve and the modulations. At the same time, it explicitly notes that circumstellar interaction is unlikely rather than impossible, and that such interaction could still be present at a lower level. That wording is not weakness. It is strength under control. It tells us that the authors are not merely selling a dramatic narrative. They are distinguishing between what the data strongly favor and what the data cannot yet completely forbid. And that difference will matter more, not less, if similar events start appearing. Because one event can transform a theory, but a class of events transforms a field. The researchers already argue that their magnetar plus precession framework can also reproduce periodic behavior previously seen in other superluminous supernovae, suggesting that SN 2024 AFAV may not be a fluke, and that the underlying mechanism could be relatively common in young magnetars. If that holds up, the implications are enormous. Yet it also sharpens the risk. Once a model begins explaining not just one object, but several, every hidden assumption inside it matters more. Are the inferred disk properties realistic across the population? Are the viewing angle requirements too restrictive? Are the magnetic field strengths and spin periods consistent with what core collapse physics can actually produce often enough? Does the same framework predict spectrocolor evolution polarization and late-time behavior, as well as it predicts brightness bumps? A powerful model invites more tests, not fewer. This is the true cost of catching creation in real time. The event does not become easier to interpret because it is exciting. It becomes harder because now it carries the weight of a possible paradigm shift. Every parameter matters. Every alternative has to be broken honestly. Every future superluminous supernova with unusual structure becomes a referendum on whether this was the first clear example of a broad rule or the most articulate member of a narrower subclass. That is why uncertainty here should not be confused with fragility. The claim is strong enough to reorganize the conversation. It is not strong enough to let the conversation stop. And perhaps that is exactly what a real birth should look like in science as well as in the sky. Not a polished conclusion, a violent beginning that forces everything around it to be remeasured. The old theory is no longer hypothetical in the same way. The easy alternatives no longer stand at equal height. The corridor has narrowed, but the meaning of that narrowing reaches beyond this single event. Because if astronomers are learning to watch newborn magnetars seize control of their supernova, they are not just solving one luminous mystery. They are opening a new way to study how the most extreme remnants in the universe first enter history. A single event can solve a puzzle and still matter most for the questions it opens rather than the answer it seems to provide. That is where this story widens beyond one death. If SN 2024 AFAV is the first birth of a magnetar caught in real time, then its importance is not limited to confirming an engine model for one strange explosion. Its larger significance is methodological. It suggests that the universe may be giving astronomers a repeatable way to study the first active months of compact remnants through light from the supernova that conceal them. That is a much bigger prize. Superluminous supernovae have long been treated as rare spectacles at the edge of stellar physics, remarkable but difficult to use because their power source remained uncertain, and their internal irregularities often looked like nuisances rather than diagnostics. This event begins to reverse that logic. The bumps are not noise. The deviations are not contamination. The irregular structure may be the instrument. If that is right, then the brightest explosions are not merely harder supernovae to explain. They are laboratories in which newborn neutron stars briefly expose their spin field strength, surrounding geometry and interaction with fallback matter before the system fades beyond reach. The story on the surface is still one exploding star. The story underneath starts to look like a new observational channel into compact object birth. That shift matters because compact remnants are usually known after they settle. Pulsars are timed long after the natal chaos. Magnetars are classified through bursts. Flares spin periods and inferred fields once the supernova glare has diminished or disappeared. By then, the violent transitional physics is already gone from direct view. A real-time magnetar birth changes the timing of knowledge itself. It moves observation upstream closer to the moment when spin-down field amplification fallback and relativistic precession are still coupled strongly enough to leave visible signatures in the escaping light. In practical terms, that means a supernova light curve may begin to do for newborn remnants what pulsar timing did for mature ones, turn repeating temporal structure into a tool for inference. And the scale of what could follow is not small. Type 1. Superluminous supernova are understood as a distinct class, typically around 10 to 100 times brighter than ordinary supernova, with magnetar engines widely discussed, because radioactive decay alone struggles to explain their luminosity. Recent modeling work also stresses that bumpy light curves are common enough within the class to demand better engine diagnostics rather than dismissal as incidental complexity. A single event can solve a puzzle and still matter most for the questions it opens rather than the answer it seems to provide. That is where this story widens beyond one death. If SN 2024 A FAV is the first birth of a magnetar caught in real time, then its importance is not limited to confirming an engine model for one strange explosion. Its larger significance is methodological. It suggests that the universe may be giving astronomers a repeatable way to study the first active months of compact remnants through light from the supernova that conceal them. That is a much bigger prize. Superluminous supernovae have long been treated as rare spectacles at the edge of stellar physics, remarkable but difficult to use, because their power source remained uncertain and their internal irregularities often looked like nuisances rather than diagnostics. This event begins to reverse that logic. The bumps are not noise. The deviations are not contamination. The irregular structure may be the instrument. If that is right, then the brightest explosions are not merely harder supernova to explain. They are laboratories in which newborn neutron stars briefly expose their spin field strength, surrounding geometry, and interaction with fallback matter before the system fades beyond reach. The story on the surface is still one exploding star. The story underneath starts to look like a new observational channel into compact object birth. That shift matters because compact remnants are usually known after they settle. Pulsars are timed long after the natal chaos. Magnetars are classified through bursts, flares, spin periods, and inferred fields once the supernova glare has diminished or disappeared. By then, the violent transitional physics is already gone from direct view. A real-time magnetar birth changes the timing of knowledge itself. It moves observation upstream, closer to the moment when spin-down field amplification, fallback, and relativistic precession are still coupled strongly enough to leave visible signatures in the escaping light. In practical terms, that means a supernova light curve may begin to do for newborn remnants what pulsar timing did for mature ones, turn repeating temporal structure into a tool for inference. And the scale of what could follow is not small. Type 1. Superluminous supernova are understood as a distinct class, typically around 10 to 100 times brighter than ordinary supernova, with magnetar engines widely discussed, because radioactive decay alone struggles to explain their luminosity. Recent modeling work also stresses that bumpy light curves are common enough within the class to demand better engine diagnostics, rather than dismissal as incidental complexity. If SN 2024A FAV is the first case where the geometry of the engine itself is becoming legible through a chirped pattern, then the next scientific step is obvious. Find more, compare them, ask which bumps recur, which do not, which events imply tilted fallback disks, which require different field strengths or spin periods, and whether the same framework predicts spectra, color evolution, polarization, and late-time behavior across the population. A single event can make a hypothesis credible. A population can turn it into structure. This is where the future of time-domain astronomy becomes part of the meaning of the event. The modern sky is no longer observed as a static archive punctuated by occasional surprises. It is increasingly watched as an evolving field of transients, whose early moments can be captured, flagged, and followed. Rubin Observatory's program is designed to image the southern sky every few nights over a decade, creating a time-lapse record of change, and its alert stream is meant to help scientists catch supernovae in their earliest stages. That matters here, because events like SN 2024A FAV are not useful only because they are bright. They are useful because they are caught early enough and monitored densely enough for structure to emerge before the evidence dissolves into late-time ambiguity. The older astronomy of rare lucky discoveries is giving way to an astronomy of monitored births, monitored failures, monitored transitions. In that world, the first real-time Magnetar birth is less a singular miracle than a proof of access. It tells researchers that the window exists. It tells them what cadence matters. It tells them which anomalies are worth taking seriously before they are averaged away by simpler models. It also reaches beyond supernova classification. If newborn magnetars can be diagnosed in this way, then superluminous supernovae become relevant to broader questions about stellar angular momentum. Magnetic field generation in collapse. The fraction of massive stars that leave neutron stars rather than black holes, and the diversity of central engines that can hide beneath similar explosions. They may even become a bridge topic, linking optical transients with high-energy astrophysics and eventually with other messengers. Recent theoretical work already treats multi-wavelength and multi-messenger signatures as a natural next step in testing magnetar-powered superluminous supernovae, precisely because the light curve alone may be only one piece of what these engines can reveal. This is the larger scale on which the event begins to matter. Not as a curiosity, but as a template. Not as a lone spectacular death, but as a demonstration that some of the most extreme newborn objects in the universe may become observable first through the disciplined timing of their concealment. The irony is almost perfect. The remnant is hidden, and yet it becomes knowable by the order it imposes on what hides it. The star explodes, and yet the real discovery lies in the behavior of what survives the explosion. The event looks like excess brightness, and yet its true gift may be a new grammar for reading buried engines inside transient light. That is why the meaning at larger scale is not simply that one theory about one class of explosions may have been right. The meaning is that the sky is beginning to reveal not just what dies, but what is born in the act of dying. And once that possibility becomes real, the final step is unavoidable. The opening contradiction of this story was that a star is supposed to die all at once. Now the deeper truth stands in full view. Some stellar deaths are not singular endings at all. They are the visible interval in which a newborn compact object seizes control of the ruins and forces the universe to let us watch. A star is supposed to die by disappearing into its own consequences. That is how the story opened, and by now, that version feels too small to survive. What SN's 2024A FAV reveals, or at least forces us to confront, is that some stellar deaths do not resolve into silence after the blast. They remain active from within. The explosion still happens. The core still collapses. The ejector still tears outward into space. But the meaning of the event no longer belongs entirely to that first catastrophe. It begins to migrate inward toward the object that survives at the center and starts rewriting the visible history of the wreckage around it. This is the final transformation in the story. The supernova is not being demoted. It is being reclassified, not as a singular ending, but as a temporary interface between two regimes of reality, the long life of a massive star and the short, violent self-announcement of the compact engine born from its collapse. That is why the phrase "birth of a magnetar ever caught in real time" carries such force. It is not only a claim about one remnant, it is a claim about timing agency and what kind of truth the universe is finally allowing us to see. The star dies, yes, but what becomes visible is not death alone. It is succession. For millions of years, the star has held itself together through fusion pressure and balance. Then balance fails. Gravity wins. The core collapses. Matter is rewritten. Rotation is compressed. Magnetic intensity is amplified. Some debris escapes. Some debris does not. The newborn neutron star emerges not as a passive ember, but as a machine carrying the stored motion of the stellar core, a field strong enough to extract that motion and surroundings, chaotic enough to turn the extraction into a structured display. The event becomes larger precisely by becoming smaller. The power that governs the explosion is concentrated into an object the size of a city. The light that crosses 1 billion years of space begins to record millisecond spin magnetic braking, fallback accretion, warped geometry, and perhaps even the dragging of space-time itself. A human eye sees a changing point of light. Hidden underneath is a system so dense and violent that ordinary language keeps failing one layer too early. That failure is part of the meaning. Every stage of this story began with an easy explanation and ended with a harder one. More brightness meant more explosion until the energy budget objected. A bright, long-lived supernova meant radioactive fuel until the accounting became absurd. A central engine explained the excess until the bumps demanded geometry. Rotation explained the engine until magnetic torque became necessary. Magnetism explained the torque until the chirped structure suggested nearby matter in relativistic motion. Fallback explained the nearby matter until fallback itself became a second catastrophe, shaping how the engine could reveal itself. Again and again, the surface story proved smaller than the story underneath. That repeated collapse of the easy answer is not accidental. It is the structure of the event itself. A Magnetar birth is not one hidden fact waiting to be named. It is a staircase of buried mechanisms, each one forcing the next into view. And that is why this event feels so important even before every uncertainty has been eliminated. It reveals a kind of continuity between destruction and creation that stellar language usually keeps apart. We speak as though stars die and remnants are left over. But in cases like this, the remnant is not what remains after the event. The remnant is what the event becomes. The old star is not simply gone. Its stored angular momentum, its failed ejector, its collapsed core, its impossible density. All of it is carried forward into the newborn object and then spent outward again through light. The death is real. The inheritance is real too. In that sense, the supernova is not just an ending. It is an act of transfer. The star hands its deep interior history to a compact object, and that compact object spends the inheritance so violently that the transfer becomes visible across the universe. This is also why the event changes the way observation itself feels. Astronomy has often been compared to archaeology, and not without reason. Light arrives late. Many of the most important things are already over by the time we notice them. We reconstruct, we infer, we look at remnants and reason backward toward vanished causes. But a real-time Magnetar birth is different. It is still inference, still disciplined, still indirect, yet it carries the emotional structure of witnessing rather than excavation. The object is not wholly settled. The central engine is still imposing itself on the light. The event is still revealing its own mechanism in sequence. The observer is not only reconstructing a ruin, the observer is watching a hidden sovereign take command of it. That may be the deepest reason this story lingers. It does not just show that nature is violent. We already knew that. It shows that nature is layered in a way that rewards patience with deeper and deeper causality. A star explodes. Beneath that, a neutron star spins. Beneath that, a magnetic field drains the spin. Beneath that, fallback matter returns. Beneath that, geometry tilts. Beneath that, space-time itself may twist. And beneath all of it sits the strangest moral in the whole event. The most important thing about a stellar death may be the new object that learns to rule inside it before the debris has even finished expanding. The first line of this story was that a star is supposed to die all at once. The final truth is harder and more beautiful. Sometimes a star dies in public so that something denser, faster, and far more consequential can be born in secret, seize the wreckage, and spend a brief season teaching the universe that an ending and an origin can be the same event seen from different depths. What matters, in the end, is not that one explosion was unusually bright. The universe has always known how to be violent. What matters is that for a brief interval, violence became legible. A massive star reached the limit of what fusion pressure and structure could defend. Its core collapsed. Its outer body was torn open. And inside that ruin, instead of silence, a new authority appeared. A neutron star, perhaps a magnetar born spinning too fast, magnetized too fiercely, and surrounded by matter too unsettled to let the event become simple. The light that followed was not just debris cooling in space. It was the visible argument between collapse and survival, between wreckage and control, between a dead star and the compact engine inheriting its power. That is why this story feels larger than a single supernova. It suggests that some of the brightest stellar deaths are not the final flash of a finished life, but the first public evidence of an object learning to govern the ruins of its own creation. The old star does not merely vanish. Its mass rotation and failed escape are concentrated into something smaller, denser, and more commanding. The remnant does not wait for the aftermath. It makes the aftermath. And perhaps that is the deepest shift in perspective this event offers. The sky is not only a place where things end. It is a place where endings become instruments, where destruction can function as disclosure, and where the birth of the most extreme survivors may be written not in direct images, but in the disciplined timing of light escaping through chaos. A star dies. A hidden engine takes command. And for a moment, across 1 billion years of darkness, the universe allows us to watch the transfer happen.